Hey everybody, this video lesson is going to be the introductory notes from Unit 9, Solids and Solutions. We're going to begin talking about the solids. Solids, as you know, have a definite shape and a definite volume. But what makes up the solid may be variable. And so we're going to talk about the different types of solids that you can encounter. This video lesson is going to cover 3 of the 4 different types of solids, with the 4th being metallic solids, which we'll cover as an entire class period in the future. The first one we're going to talk about is the ionic solid. Now, most of this will be review for you since we talk about ionic bonding pretty regularly in this class, but it's important to be able to use ionic bonding and compare it against the other 2 types we're going to talk about today, the covalent network solid and the molecular solid. Now, the principal difference between ionic solid and the other 2 I just mentioned is how the particles are held together. Ionic bonding, remember, are electrostatic attractions of opposite charged particles. So you got a positive and a negative particle held together. And ionic solids form crystalline structures that are known as crystal lattices. A crystal lattice and the ionic crystals basically form an alternating positive and negative ion, and every positive and negative is surrounded by every positive is surrounded by negative ions on all sides. And so it forms this alternating pattern of positive, negative, positive, negative, positive, negative. And remember, this is in 3 dimensions, so there's layers coming out at you and layers going back into the screen. The results of this crystal lattice is that it has very high melting points, thousands of Kelvin before it will melt. Now, of course, all crystal lattices are a little bit different. Some melt at lower temperatures than others, but overall, crystal lattice from ionic solids have incredibly high melting points. But one thing that sets crystal lattices apart from the other types of solids is that it does not conduct electricity in its solid state. And that makes sense because if you think about it, the ions are holding on to their electrons, and so the attraction is just simply a positive-negative attraction between ions, and the ions aren't actually touching at all. Their electron orbitals aren't overlapping to create covalent bonds. Sodium is holding on to its electrons, chlorine is holding on to its electrons, and there's no ability to conduct electricity between the 2 ions because there's no touching or overlapping at all. In order for electricity to flow, the electrons need to be able to jump between the particles or travel over a bridge, so to speak, and so ionic solids just don't allow for electrons to travel. Final thing I want to say about ionic solids is that when the ionic bonds break, which requires a lot of energy to do so, but when they do, ionic solids are very brittle, which means they break very sharply. And because of this, when you break a crystal lattice, it makes nice flat edges and sharp corners. Now, if you read about this in the textbook, which I highly recommend that you do, and it's chapter 12, section 5, they're going to go on and talk about the different structures of the ionic crystal lattice, and you do not need to be responsible for that information. It's really dense and not really useful for our purposes in AP chemistry. So the whole concept of different types of crystal lattices is not what you need to know for this class. But the basic ionic substance, how it's held together, and the properties that it exhibits are important, and so I cover those here. The next type of solid I want to talk about is called a molecular solid. This is chapter 12, section 6 in the textbook. There's not much to say here, so this will be quick. These solids are held together by weak intermolecular forces, the attraction between molecular solids like the dipole-dipole and the hydrogen bond. And because they're held together by the weaker forces, they have extremely low melting and boiling points. In fact, most molecules exist as liquids or gases at room temperature because their intermolecular forces are so weak, but there's a handful that are solids. If they are solids, the chance that they stay solid at high temperatures is pretty low. Your examples of molecular solids are things like ice or carbon dioxide in the form of dry ice. But if you lower the temperature enough, these molecules will start to shift and form crystals of their own. In fact, ice is a crystal, and if you've ever looked at a model of ice, it's a 6-sided hexagon that is the principal shape behind ice crystals in the form of snow. And so if you ever look at a snowflake under a microscope, you'll see that it has 6 sides. And that's because of the crystal at the middle is a 6-sided hexagon sort of shape. So what you're looking at now is a picture of an ice crystal. This is a model that I have back in the cabinet, but you can see that these are alternating waters, and the purple is the dipole interaction of the hydrogen bond. So you got 1, 2, 3, 4, 5, 6, or 6 different water molecules, and they're held together by their dipole-dipole interactions between the 6 different structures or 6 different molecules of water, and you get this hexagon. You can see just like that. Now they are connected to other crystals of water, also in 6-sided hexagons, and it creates this structure, which is the principal reason why water in ice form floats on its liquid self, because as you know, or maybe you don't know, so I'm about to tell you that solid ice has less density. It actually expands as it freezes and is less dense than the liquid self, so it floats on top. It's because we have these vacant areas in the middle of the ice crystal that can form air pockets, and so the ice is actually expanding with the same amount of mass, so the volume increases but the mass stays the same, and so you get a floating ice crystal. The last things that I want to say about molecular solids is that, as I already mentioned, but I might as well write them down, they have low melting points, and because the particles, again, don't really touch, the electrons don't have a chance to flow, they don't conduct electricity in their solid state. So the last one we're going to talk about is called the covalent network solid, and it is one of the more interesting of the 3. Covalent network solids are held together by large networks of covalent bonds. So imagine an ionic crystal lattice, but instead of alternating positives and negatives, you get basically connections of covalent bonds. And because they're actual covalent bonds connecting atoms, it's much stronger than intermolecular forces, resulting in much harder substances compared to molecular solids, and have extremely high melting and boiling points compared to their molecular solid cousins. I snagged this screenshot from our textbook, but an example of a covalent network solid is diamond or graphite. Both of these happen to be covalent network solids of carbon. You can see that in diamond, you've got an ionic crystal, a covalent crystal of alternating carbons making 6-sided hexagons as well. Graphite likewise has hexagons, but the difference in the structure is slightly variant. So we'll talk about the difference here. But the fact that each carbon is surrounded on 4 sides by other carbons result in this hexagonal repeating pattern, which caused diamond, as you know, one of the hardest natural substances on Earth, can scratch anything because it has sharp corners and it's very hard and high melting points. And so you can say that covalent solids and ionic solids have fairly high or very high melting and boiling points. They also have very strong bonds. They're incredibly hard. They're very comparable. Anyway, let's talk about graphite. So you still have this 6-sided structure, but you've got basically sheets of carbon held together by these intermolecular forces. And so it's less strong because these carbons aren't surrounded on 4 sides, but rather just 2 sides with covalent bonds. And so the intermolecular force between the carbon sheets allow graphite to kind of slide off. So imagine pencil lead. As you run your pencil along a paper, you're basically sliding off sheets of carbon, sheets of carbon, sheets of carbon as you go. And eventually your pencil gets worn down. You have to sharpen it again. But that's because you're actually losing mass in the form of carbon onto your paper. So the sheets just kind of slide off. So let's zoom back out here and talk about some properties of covalent network solids. And so as I mentioned before, they're high melting points. The thing that sets them apart from their ionic counterparts is that they have some conductive properties and are sometimes used as semiconductors. Remember, we talked about in hybridization that these bonds between the carbon are the result of hybridized orbitals, the sp3 orbitals, and because the electrons are overlapping in those sigma bonds, you can get actual electrons being transferred between the particles, which is why we were calling them semiconductors. They're not the best conductors like metals are, but electrons can pass between the particles fairly, not easily, I'll say, but it can pass, and as a result, we've got semiconductors. The last semiconductor and covalent network solid that I want to show you is actually this neat little one that I have a model of, and so I took a picture of it and showed it here. This is what is known as a buckyball, which is a form of carbon, and as you can see, instead of having a crystalline solid that repeats time and time again like diamond, you get an actual finite crystal, which is known as a buckyball, which is actually Buckmeister fullerene, but it is a synthetically produced carbon compound developed, I think, by University of Wisconsin, which is why it's got the name Bucky, but I can't be sure about that. I should probably fact check that before I actually say it in a video, but oh well. But a buckyball is a alternate form of fuel and can be burned to create lots of energy in a small, dense carbon rather than, say, like octane gasoline. This is more efficient. You get more energy per fuel molecule, and it's kind of interesting. I don't know much about them, but of what I know, it's kind of the cutting edge of fuel technology as far as carbon-based fuels go. It's worth mentioning that there's one more carbon-based covalent network solid called carbon nanotubes, which are strong, long tubes of carbon, kind of like sheets of carbon that are wrapped around, making hollow tubes. They're incredibly strong and used and can be woven into fabrics to create strong fibers that don't break or puncture very easily, and also can be used in things like airplanes, like wings and other parts. So anyway, those are all covalent network solids. Most of these covalent network solids I've talked about were carbon-based, but there's some that are silicon-based and others like silicon dioxide, which is quartz, which is another covalent network solid. Anyway, this video lesson is finished. It went a lot longer than I thought it did because I just talked about random stuff, but hopefully you enjoyed it and it was informational. And next up, we'll talk about metallic bonding. Thanks for listening.